All right. So 13.96. The speed of a wave on string that's tied down at both ends is this. If the fundamental frequency of the string is this, what is the length of the string? So I think everyone has the same numbers on this, right? Okay, so I will not be doing a lot of math so that you have to actually do some of it yourself. All right? But let's talk through it. Let's especially look at the Y. So 13.96. I think one thing that can really help with these is getting a picture of it or thinking about what it would look like. So tied down at both ends. If both ends are fixed or tied down, folks, remember you're welcome to do your own work and not pay attention, but please do be a little quieter. Hard to some people to hear. So if it's tied down at both ends, how much is it moving at the ends? It is not. So what part of a standing wave would have to be at the point that it's not moving? A node. And it says its fundamental frequency. And that fundamental part says, hey, it's as short, it's as little of a wavelength is on there as possible. So what's the littlest amount from node to node? Half. So if I was to draw it, I draw a node and a node, and on the end of a vibrating string, you're always going to have node to node. Think about when we did the yellow rope, or we did when you played around in the back there. And the fundamental says the smallest part of the wave, which would be that, which means this is equal to half lambda. Does that look like a kid's game at all? Jump rope. Yeah. Also, jump rope is a standing wave? Oh. You move your hand at the right frequency. See, you knew physics, you didn't even know it. So, I would put things in here like must have nodes at ends and a standing wave is formed. And now what they tell us is the frequency, its fundamental frequency of this string is 65 hertz. So that means when we have this pattern here, when we have that half a wavelength equal to the length, that's the frequency of that wave is 65 hertz. Okay, so they tell us the frequency is 65 hertz. They also tell us if this is the length of the string, right, that L equals half lambda. And they told us the speed of the wave, I believe. 32 meters per second. Whoops, wrong one. 32 meters per second. What else do they tell us? I wish there was something, an equation that related frequency and wavelength and speed. Our old friend, V equals lambda F. So now all you need to do is substitute in there, and you can find out lambda and then find out L. Or if you do a little bit of fancier math, you can find out L directly. Give it a try. Let me know if you need help on the math. All right, the next one that was requested was 13.97. And again, I think this is one where we all have the same numbers, so I'm going to let you do the math so that you don't get that robbed from you. But it says the first harmonic of a string tied down at both ends. Oh, if it's tied down at both ends, what must be at either end? A node. And therefore, since it's at the first harmonic, it's at a standing wave. Oh, wait, this seems a little familiar. Oh, it's kind of like the last one we did, but slightly different. So 13.97. But I would do something very similar for my y because I'm at the first fundamental. What would the second fundamental look like? What do you think? Yeah, it'd be a whole wavelength, right? It would have the two antinodes rather than just the one. Remember, you have node, antinode. But again, we have half lambda equal to L there. And the last problem. So I'm being lazy, saying, tell me, read the last problem. And length of the string is this. Do we know the frequency? 26. We know that L equals half lambda. We know L. 0.83 meters. Look, Jacob, we're working in meters. And we know that the speed is lambda f again. All right, let's look at 13.53 here. I think the whole understanding of this, the whole why of this one would be drawing the picture. Since it's a guitar string, since it's a string, what must be at either end if there's a standing wave on it? So there must be a what? A fixed end, which on a standing wave, Kathy, would give you a Miss Murphy. What would you have? What part of the standing wave would be at the end of this chord since it's a fixed end? A node, correct. So every time we have a vibrating string, it goes from node to node. And it's saying two antinodes. So I have an antinode and then another antinode. So there's my drawing, right? Node, 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 antinode, antinode. Oh, and this is the length of my string, right? How much of a wavelength is in that length? One wavelength. So that's the length, and that's also lambda. And I think if you have that, you're probably good with the whole thing. Let me know if you need help with that one. All right, so looking at 3.98. That's the last problem that was asked for. String is tied down at both ends, has the length of this, and its first harmonic has the frequency of this. If the length of the string is increased while all other variables are kept the same, does the first harmonic frequency increase, decrease, or stay the same? Well, let's see. What would cause the frequency to increase? Excellent. Oops. So if the wavelength, did it say increase?
It says
Increase.
if the length of the string increases.
If, did it? Okay. If that increased, then the frequency would decrease.
Oh. Okay.
Because remember that the equation v equals lambda f does not say that the speed is based on the wavelength and the frequency. You have to think about it as the wavelength and the frequency are based on the speed. That's kind of one of those critical understandings that's beyond just using the equation. So, what determines the speed of this wave? The medium. The medium. So, and the medium is like how heavy a string it is, what tension it's under, you know, how thick it is. Has any of that changed? No. So, has the speed of the wave changed? No. So, that's one thing I definitely look for in a Y on this problem is that speed is constant since medium does not change. And so if the speed is constant, that medium doesn't change, length of the string is increased, which would increase the wavelength. All of it is the same. Does the first harmonic frequency increase, decrease, or stay the same? So we just increase the wavelength, therefore the frequency must decrease. And then calculate the first harmonic frequency of the string whose length is increased to this. So we are going to use v equals lambda f, but we said, hey, in the first case, the speed stayed the same as in the second case. Therefore, wavelength 1 times frequency 1 is the same as wavelength 2 times frequency 2. And so you look at your problem setup, do we know the original wavelength? Yes, we do, because we know the length, right? And like our other times, we know the string looks like this, right? With node, antinode, and node. And we know the length of the string is 1/2 lambda. So you do know the wavelength ahead of time, you know the frequency ahead of time. You're told, I believe, the wavelength afterwards, right? Yes. And therefore, you can figure out the frequency afterwards. So a little substitution there, a little algebra, and you're all set. I think that's all of them.